All right, welcome everyone. Thank you for being here. My name is Aaron. I'm on the National Climate Assessment team here at the U.S. Global Change Research Program, or USGCRP. Before we get started, I want to draw your attention to the note in the chat box. Microphones are disabled for all participants, but if you have questions or comments throughout today's session, please enter them in the chat. If you have any technical difficulties, please contact Eliza, who is our tech support person today. Please note that all participants are expected to be respectful and considerate towards others per the USGCRP Code of Conduct. Next slide, please. All right, I'll kick off our webinar today with some background information about the National Climate Assessment before turning it over to the Land Cover Land Use Change chapter authors. Next slide. The U.S. Global Change Research Program was mandated by Congress in the Global Change Research Act of 1990 to assist the nation and the world to understand, assess, predict, and respond to human-induced and natural processes of global change. This program convenes 15 agencies to advance the climate and global change science and to provide useful and usable information to decision makers. Next slide, please. The same law that established the program also mandates a periodic scientific assessment, known as the National Climate Assessment, or NCA. NCA is a quadrennial, every 4-year report that analyzes the effects of global change on several sectors: the natural environment, agriculture, energy, land and water resources, transportation, human health, social systems, and biodiversity. USGCRP is charged with assessing current trends, as well as projections for the next 25 to 100 years. The NCA is used by organizations and individuals for a variety of purposes, including national policymaking, risk management in the private sector, local mitigation, adaptation planning, as well as by practitioners, utility managers, and educators. Next slide, please. NCA authors are charged with reviewing a large body of scientific research from diverse information sources. They synthesize that information, examine the confidence in our scientific understanding, and evaluate uncertainties. NCA5 was written by 500 authors and 260 technical contributors from every state in the nation, as well as Puerto Rico, the U.S. Virgin Islands, Guam, and Palau. The NCA is designed to be policy relevant. Authors distill their findings into accessible language framed around risks to people and important resources. But that being said, the report's strictly not policy prescriptive and does not advocate for particular viewpoints or policy measures. The NCA uses a range of future projections to help decision makers understand the full extent of possible risks that can be avoided or reduced under different scenarios, and leaves it up to the decision maker to ultimately decide their risk threshold. The assessment is compliant with all applicable federal laws and policies, including the Global Change Research Act, as well as other laws that govern things like information quality, accessibility, and transparency. Finally, the report process involves extensive review, including several opportunities for public engagement, a review by the National Academies of Sciences, Engineering, and Medicine, and several government science reviews. Next slide, please. Let's take a look at the NCA5 table of contents. Like previous NCAs, NCA5 covers national level topics, regions, and response actions. The report opens with an overview, which is followed by 2 chapters dedicated to the physical science of climate change. Then there are the national topic chapters, the 10 regional chapters, and 2 response chapters, although response actions are discussed throughout the report. The NCA table of contents has evolved over time, informed by user input. NCA5 added 2 new chapters, one on economics and one on social systems and justice. We also have 5 new focus features on compound extreme events, Western wildfires, COVID-19, supply chains, and blue carbon. We have several appendices, including a new one dedicated to indicators. All right, now that we've gone through some introductory background, it's my pleasure to introduce Peter, the chapter lead of the Land Cover and Land Use Change chapter, who will lead us through the remainder of our webinar today. Thank you.
Aaron, thanks very much. And thanks to everybody who's able to join us today on behalf of the whole authorship team and our fantastic support from USGCRP. Welcome to the seminar. I want to start out by giving you an overview of how the chapter was guided in terms of identifying the topics of importance, and then the framing for how we address those topics. And that was using our risk-based framing approach that led us to our key messages. The essence of that approach is to identify the things that are important to us and then identify the ways in which those important topics are threatened by climate change. And this was a really helpful approach for our chapter team in coming up with the topics that we covered. Those topics, sorry, included three key messages. And the first was a focus on the value that we place on the goods and services provided by the land system. So although our chapter is looking at land cover and land use change, we're looking at that in the context of a fully integrated land system and how, in this case, the goods and services provided by that system are threatened by climate change. The second key message addressed the importance of the land system resilience, so the ability of the land system to withstand disturbance and return to its previous state is one way of defining that resilience. And changes in climate and changes in land use are both affecting the ability of that land system to be resilient. The third value that we assessed was the value that we place on being able to make choices about how we use the land and how we deploy different land use decisions. As we move toward the necessary actions of mitigation and adaptation in response to a changing climate, we are identifying ways in which those options and those choices are constrained increasingly as we move into the future. So I'll say a few introductory words about some of the data sets that we use to evaluate the land use and land cover information over the US as we dug into our chapter details. We use the LC map data set as a primary source of information for land cover and land cover changes over time. This is showing you the diversity of land covers represented by that data set over the US. A benefit of that data set is that it also looks at changes over time. And this is just showing a quick view of how the different categories of land use and land cover are averaged over the period of 1985 to 2020, and then how those categories have tended to change in terms of percent change from their starting point in 1985. And the main point that we were drawing from these results is that the developed area has increased consistently over that period, while other areas have increased and decreased with an overall trend in decreasing tree cover as a dominant response there. We were also able to assess the frequency of changes in these land covers from those data sets and looking at different drivers for the frequency of changes. For example, in the region around Columbus, Ohio, changes resulting from development expanding away from the core of the urban core there. In the Red River area, lots of forest management going on there is leading to multiple changes in land cover over time. And for example, over the Yellowstone region, large disturbances such as wildfire leading to significant changes in land cover over time in that region. So I'll jump into then the goods and services key message 1, and then I'll be turning this over to other authors to look at key messages 2 and 3. And the key point that I want to make for the key message 1 is that the goods and services provided by the land system are diverse, and all of them are being threatened to some extent by climate change, and in particular by changes in the intensity and frequency of extreme events such as rain, droughts, changes in temperature, high temperatures, as well as disturbances like fires and urban floods. And the kinds of goods and services that we're referring to here include the ability of the land surface to support infrastructure, agricultural production, forests and all of the goods and services that forests provide, biodiversity as a good in itself, carbon sinks in terms of the ability of the land system to take up carbon that's released into the atmosphere from fossil fuel emissions, and provide the service to all of the world through absorbing that carbon, and the benefits of human health. So all of those goods and services are threatened. We took a particular look at the impact of wildfire as an example of a topic where we can see particular threats, especially in Western forests. And we also note that spiritual practices, the use of land systems for recreation, and the use of land systems for sustenance are all also being threatened by climate change. So I'll take a couple of minutes then to show you some examples of the kinds of effects that we're looking at within the chapter. And this is an example from the 2018 debris flows that happened in Montecito, California. And this was following a period of intense rain in January of 2018 in that region that occurred over the area that was burned the month before in December 2017 by the Thomas Fire. So a very large and damaging fire followed by extreme precipitation in this region led to debris flows, which caused a considerable amount of damage and destruction. And the point here is that we're seeing these kinds of compound events as an indicator of the damage that climate change is doing to the values that we place on all of the topics that I mentioned: infrastructure, agricultural production, forests, the ability of these ecosystems to protect human health. All of that is threatened by this kind of compound event, and it's one example of many that we point out in the chapter. Another topic that we looked at in detail in the chapter was the ability of the land system to provide the goods and service of climate change mitigation themselves. So we know that half of the carbon that humans put into the atmosphere through fossil fuel and other kinds of actions is taken back out of the atmosphere by the combination of ecosystems on land and biological and physical processes in the ocean. Of that 50%, half of it is due to the response of land systems to that change in CO2 concentration. And so there's a tremendous service that the land systems are providing to all of humanity by taking up that carbon from the atmosphere and preventing more climate change than we would otherwise have seen. And the point that we raise in the chapter is that the ability of these systems to do that is very tightly connected to not only the current land use, but also the trajectory of land cover and land use that's led up to the current state. And depending on what kinds of disturbance have happened on a particular piece of land, or what kind of management practices have been in place over time, you can have very different characteristics of whether that land is acting as a source or a sink. And so the protection of that source and sink is an important aspect of the threat that we were identifying in this work. So I'm going to transition now to our second key message, and I will ask Huiling Wang to take over.
Thank you, Peter. So the second message, we focus on how changes in climate and land use impact the resilience of the land system. The statement that we put in here is that changes in climate and land use affect the resilience of the land ecosystem, and therefore the fate of the service they provide, like what Peter already talked about in the first message. For example, drought could impact the land productivity, both in terms of the forest, in their ability to store carbon, or in terms of the cropland crop yield. And the point that we want to talk more here is about the interaction between climate and the land use changes, and how these interactions present challenges as well as opportunities. I'm going to speak to this a bit more.
Guiling, I think you put yourself on mute by accident.
Oh, sorry. I'm going to elaborate on this point using the diagram on the next page. So we look at a very basic figure here. It shows the primary land use, land cover changes, and their interaction with the climate and their impact on the ecosystems. Here, if you look at the figure in the middle row that shows different types of land cover. There is dry land, grassland, cropland, urban area, and forest. And those black arrows between those different land types indicates the type of land cover changes or land use. And the gray arrows pointing up and down, they show the impact of feedback to the climate and the impact on the ecosystem. So Peter has shown that the major change in land use in the past is an increase of the urban areas at the expense of the cropland and the forest. So I'm going to focus on these dynamics here. Of course, the other type of land use, land cover changes are also important. And the reason, so some of the gray areas has words box related to it to indicate the type of feedback or impact, and some did not. And the reason is we only show the impact that we feel that is supported by evidence, not that the others did not have impact. Okay, so I'm going to first talk about urbanization. This is probably the most well-known in terms of how urban heat island impact the temperature, of course, and the urban areas, it also impacts precipitation regimes, primarily increase the intensity of extreme rainfall. And also we probably have heard a lot about flooding in the urban areas because of the change of the soil to impermeable surface. So those in terms of the heat, increasing extreme rainfall and flooding are what we consider the impact of urbanization on the climate, or the feedback to the climate. And then in terms of the forest, there has been loss of the forest to urbanization, and there has also been places where there has been abandonment of cropland, which then grow back to forest, and we call those the new forests. So the presence of trees or forest has a cooling impact on the local environment, and it could also bring more rain. And you can imagine that the loss of the forest then would be the other way around. If you have a loss conversion of the forest to urban land, then we expect to see increase of temperature, probably decrease of the rain amount, even though you might look at a more intense rainfall. And in terms of the new forest, when we lose forest is a abruptive loss of ecosystem service, but when we gain the new forest, for example, as a result of agricultural abandonment, there is going to be a very slow recovery process of the ecosystem service that you expect from the forest. And I'm going to switch to the cropland area here. So in terms of the cropland, there has been changes, gaining new cropland from forest area, and there is also conversion of grassland to cropland. And in other places, you might have loss of the cropland because the land is no longer productive, and then they will go back to forest or return to the natural grass. And those processes are going to take a very long time to recover. And in terms of the impact of cropland or agriculture in general on the local climate, there have been studies showing that when you have intensification of cropping activities, you would trigger or cause a cooling impact to the local environment, as well as increase of rainfall. So that's what we're showing in those text box there. And when you have a conversion of natural landscape to cropland, of course, you are going to experience a dramatic loss of the ecosystem service the natural land has provided. Of course, you gain crop yield, productivity. So it's a different types of service here we are looking at. And as I mentioned already, sometimes the cropland is no longer productive, you abandon, and that leads to sort of growth of new grassland. And again, that the recovery of the ecosystem is a really slow process. And I want to see a little bit about the dry land. And when we look at conversion of natural vegetation to dry land as a result of human activities or a natural desertification process, and that is going to cause an increase of temperature and a decrease of precipitation, therefore contribute to the increase of heat and drought risks. And again, the conversion from grassland to dry land, and that leads to a dramatic loss of the ecosystem service provided by the grassland. So that's the overall message or explanation for ORCAM 6.2. And again, I want to emphasize that in terms of the feedback and impact, we only present the ones that we think there is a consensus in the literature, and that doesn't mean the other activities do not have an impact. Thank you.
Thanks, Guiling. As we move to the ORCAM 6.3, I'm going to turn this over to Louise Cheney, and then we'll hear from John Field as well. Louise.
Hi, everyone. So our third key message is that mitigation and adaptation priorities will increasingly constrain future land use options. So the future of land use in the United States will depend on how energy and agricultural technology evolves and how the climate changes and the degree to which we prioritize the climate mitigation and adaptation and land use decisions. The United States cropland area had been declining, but has rebounded somewhat over the last 1 to 2 decades. Future cropland needs will depend on uncertain factors such as agricultural technology improvements, dietary shifts, and climate change impacts. Decarbonisation will require continued expansion of solar and wind energy generation and transmission infrastructure, and may also involve some very large land use changes toward land-based mitigation measures, including reforestation and other natural climate solutions, as well as bioenergy crops. And so an important part of this key message is really that our future land use choices are going to involve many really competing and increasing demands for the land in order to support our land needs for agriculture, for housing and infrastructure, for conservation of natural lands, in order to preserve biodiversity and to preserve recreational opportunities and for spiritual sustenance, as well as our land choices towards climate mitigation and adaptation. The next slide, please. Okay, so figure 6.8 considers these future land use choices towards mitigation and adaptation, with the horizontal axis showing land use choices that increase our adaptation to climate change, and the vertical axis showing land use choices that contribute to mitigation of climate through reduced emissions and more carbon storage. So the top right quadrant of the figure shows some of the future land use choices in different colors, with the green ones representing future land use choices that are headed towards mitigation of climate change, such as reforestation or afforestation, and bioenergy crops using carbon capture and storage as well. On the other side, we have the blue land use choices, which are more towards the adaptation towards climate change, such as coastal infrastructure planning and prescribed fire. And then in between, we have land use choices that do some towards mitigation as well as adaptation, such as the coastal wetland restoration and increasing trees in urban areas. The lower quadrant of the figure shows land use choices that can result in more emissions and less carbon storage, such as deforestation, or more maladaptation, such as development in floodplains, or some that do a little of both, such as reduction of green space in urban areas. And all of these future land use choices towards mitigation and adaptation take place in a background of different factors that drive these choices, including improvements in agricultural technology, changes in income, changes in food waste and dietary changes, and international cooperation and governance. So next slide, please. Okay, so we can use scenario analysis to explore different possible land use futures under a range of different driving factors. These scenarios are known as shared socioeconomic pathways, or SSPs, and they consider different climate mitigation storylines in a consistent way between the land use choices and choices in the energy system and emissions reductions, and allow these systems to evolve together so that we can investigate how the impact of our different choices in these scenarios. There are multiple different driving factors in these scenarios, including changes in population and technology and governance. And here, this figure 6.9 shows what future land use trends in the USA would look like based on a range of different future scenarios. There are 8 different scenarios included in this figure for 3 different time points in the future, as well as a set of baseline values in the year 2000. And so most of these future scenarios show increases in urban area in the future, shown in the red land use category in the figure. Many of them, or most of them, show stable or declining areas of food crops in green. And that is mostly due to underlying assumptions in the scenarios about continued increases in agricultural technology improvements. The scenarios that have lower emissions tend to have higher areas of forest due to reforestation policies, and tend to have lower areas of grazing land due to changes in diet towards fewer animal-based calories. whereas the scenarios with higher emissions tend to have less forest and more grazing land. And then there are also, in many of these scenarios, there are somewhat large areas of land use change towards bioenergy crops, and these are used to offset fossil fuel use in other sectors. And as you can see, that those are the gray lines, and in some of these scenarios, they're projected to be fairly large. But it is important to remember that these scenarios are not predictions of our future land use. Rather, they're tools that we use to consider what our land use choices might be and how each different land use choice has an impact on the other ways in which we can use the land. So that's sort of how we approach the use of these scenarios. With that, I'll hand off to John for the following figures.
Okay, thank you, Louise, and good morning, all. We just have a couple more figures that we want to highlight for you today. This next one is thinking a little bit about the future deployment and scale up of renewable energy production in the US. And so decarbonization scenarios are in pretty strong agreement that we're going to see a lot of growth in wind and solar production domestically in order to electrify our economy and reduce our emissions. And this is something that the general public is probably going to be able to see more so than they see and interact with the existing fossil fueled energy system. So the map here in figure 6.10 just illustrates this in the context of wind in pink and solar in green, showing in the darker colors the existing locations of such generation facilities, and in the lighter colors, how that might expand into the future. And as time goes on, we're expecting additional wind development in a corridor throughout the central US from Iowa and Illinois down into Texas and New Mexico. And then we see already, and we'll see expansion in the future of photovoltaics on the Atlantic seaboard and the Southeast, and then into California as well. And this inset just gives a little illustration of some wind and solar facilities within an agricultural landscape existing in Illinois right now, showing what that looks like and scales relative to, you can see crop fields in the background imagery there. Wind is going to have a large visual footprint in the future. It's going to be visible over as much as 130 million acres, which is a very, very large area. But as you see on the next slide, there's a big difference between the visual footprint and the actual physical footprint of wind systems. So the actual amount of land that they occupy is only on the order of a percent maybe of the total visual footprint of these wind facilities. And so as a result, they integrate relatively well into existing cropping and agricultural systems. Solar is perhaps a little bit more challenging. It's currently a dedicated use of land, displacing other uses of land, though there's a lot of ongoing research interest in things like agri-photovoltaics, this idea of maybe we can site these photovoltaic systems in ways that preserve a dual use of the land that allow animal grazing or row crop production between rows of solar panels. In the end, solar is, even when it's fully built out and supporting a fully renewable electrified economy, it's expected to be a relatively small land use compared to others, which is why it wasn't included on the previous figure 6.9 that we were looking at. So it might occupy on the order of 1 or 2 or 3% of cropland, but probably nothing beyond that. One final point to highlight that was mentioned in our key message, there's potentially more of a trade-off and more of a conflict between agricultural land occupation and some other land-based mitigation measures. So there's a lot of interest in decarbonization plans for carbon dioxide removal and actually taking some of the carbon that's currently in the atmosphere and trying to store it through regrowing forests in different areas, or potentially carbon negative biofuels and bioenergy and other engineered solutions. These are represented to a large degree in the integrated assessment modeling that's been highlighted in previous figures. So it is potentially a very large use of land and a very large growth area in the future, but ultimately it's somewhat controversial and speculative. There's limited existing experience with these technologies to date. There's, I think, a lot of hope and a lot of potential there, but ultimately the ultimate scale of those technologies is still uncertain, and there's a big divergence between what's on the ground currently versus what's represented in the models. So that's something to pay attention to into the future. And I think I'll leave it there. Thank you.
Great. Thank you to Guiling and Louise and John for the presentations there. And I'll just note that we also have two other authors online to help with the Q&A. That's Jay Zhu and Chaley Hoover. So I'll stop sharing and turn it to Aaron.